Yeah, next topic is amperometry. Also, amperometry, as the name indicates, is the measure of ampere, okay, which is current. Yeah, by measuring the current, you can do the analysis. But in this time, in this case, at constant potential, okay. So by you apply the constant potential to the system, and then you measure the current as a function of time, yeah, not a function of potential, because potential is constant, okay. And this technique is very useful, okay. So you may not be confused with the potentiometry, okay, which is the basis of ion selective electrode. In potentiometry, current is zero, okay. You measure the potential, okay. You measure potential not as a function of time, but you measure potential as a function of analyte concentration, okay. Depending on the next equation, okay, then the potential changes with respect to the analytic concentration. Yeah, that's the potentiometry. But in amperometry, you apply the constant potential, and then you measure current as a function of time, and also this current uh, is proportional to the analyte concentration. Okay, yeah, and that's the basis of analysis. Okay? And one example is the oxygen. To solve the in solution, oxygen concentration can be determined by amperometry. Okay, and many biosensors are based on the amperometry. For example, you'll see here in the below, glucose sensor. Yeah? That is based on the amperometry, yeah? By measuring the current, and current is proportional to the analyte, the concentration. Okay, yeah, and there are many types of amperometric sensors. Okay, on the market, and here is also important is the selectivity. Okay, let's assume you have many things, many species in solution, and then you want to measure the one specific species concentration. Yeah? So this amperometry, to apply this amperometric to the sensor, you know, is important to give, say, a selectivity to the system. Okay, so for the selectivity, you use the biomolecules like enzymes, antibodies in the DNA for highly selective response to one analyte. Okay, and then you measure the current. Okay, usually, in electrochemistry, we receive electric signal, okay, but optical signals also may be used, okay. Yeah, that is based on the basis of spectrophotometry, okay. Here is the electronic noise. Electronic noise is a mimic our nodes, yeah. This electronic noise is that you have the analyte, okay, and then our nose smells the species, okay, and then so with amperometry sensors are like electronic nose, okay, and based on conductivity. There are not only conductivity, but electron nodes may be based on the amperometry, okay, the current. Yeah, here is a good example of amperometry, which is blood glucose monitoring. Okay? And a lot of people, yeah, in the world mm, are suffering from diabetes. Okay? And in our country, I think several, maybe 4 5 million people are suffering from diabetes. Okay, in America, the number is much higher. You know, the number is more than several tens of a million people. Okay, so diabetes, uh, there is too much glucose in blood. Yeah? To make taking measurement of glucose concentration in your blood is very important. Okay, and that glucose measurement must be done at least several times in a day, right? After you eat breakfast or lunch or dinner, and then usually diabetic people they measure their blood the concentration. Okay, and now question is how to measure the glucose concentration in blood. So there have been developed many the glucose sensors. Okay, still this one, this glucose sensor is still a very hot area for the researchers. Okay, and among many the detection method, the method based on electrochemistry, usually amperometry, is mostly well known. Okay, and then the glucose sensor has been developed. Okay, first generation, second generation, third generation. Okay, and um, since glucose sensor market is really big, a lot. The market is very big. Okay, let's consider how that glucose sensor has been developed. Okay, the early glucose sensor is based on this reaction. This is glucose, and it reacts with the oxygen. Okay, using glucose oxidase. This reaction it proceeds very readily. Okay, as a result, this hydrogen peroxide is produced. Okay, the glucose plus oxygen in the presence of glucose oxidase gives you a gluconolactone. This is oxidation product of glucose, and as a result, hydrogen peroxide is produced. And without the enzyme, this glucose oxidase, oxidation of glucose is negligible. Okay, so you have to use the glucose oxidase. Okay, without this enzyme, this reaction doesn't proceed readily. And also, one of the main reason to use glucose oxidase is that this glucose oxidase is enzyme, one of the enzymes, and it is selectively react with glucose. Yeah? Although there are many species in blood, okay, glucose oxidase only pick up this glucose. Yeah, that's the reason. Okay, but how do we know the concentration of glucose? Okay, so idea is to measure this hydrogen peroxide concentration, and then we can relate this hydrogen peroxide concentration to this glucose concentration. Okay, you understand? And as you know, the hydrogen peroxide can be oxidized and also can be reduced. Either way is possible. Okay, but which one do you prefer? Now, oxidation or reduction of hydrogen peroxide? Yeah? The answer is that oxidation of hydrogen peroxide. Okay, that's the usual practice. Why? Hmm? Why not reduction? Okay, yeah, hydrogen peroxide is readily reduced to water. Okay, but that reaction is not employed. Why? Because when hydrogen peroxide is reduced, and also if there is a oxygen molecule, and oxygen molecule is also reduced, right? So usually the oxygen concentration in blood is quite high. Yeah. So when you try to do the reduction of hydrogen peroxide, and then you know that is may not be accurate, yeah, because of the interference of oxygen. Okay, so usually hydrogen peroxide is oxidized. When it is oxidized, it is gives oxygen, this gas. Okay, and then two electrons are produced. So by measuring the this current, okay, and then the current is proportional to this hydrogen peroxide concentration, and when you determine the hydrogen peroxide concentration, that is the glucose concentration, because there is a one-to-one reaction. Okay, very simple. So to the oxidized hydrogen peroxide, you apply 0.6 volt versus silver chloride. Okay, I think at the potential at a neutral pH. Okay, and then the measured current is proportional to the hydrogen peroxide concentration and also proportional to the glucose concentration in blood. Okay, yeah, that's the idea. Okay, this is a result, a very nice result. X-axis is glucose concentration here, and the y-axis is current. Okay, it gives a very nice, the straight line, right? There is one big problem, yeah, with all type sensor. Okay, this type of sensor depends on the this oxygen gas. Okay, but what if this oxygen concentration in blood is not enough to whole to totally oxidize this glucose? Okay, you understand? Huh? To utilize this reaction, you have to have enough oxygen molecules in blood. Okay? Then, if oxygen molecule this concentration is less than that of glucose, and then your measurement may not give you a precise answer. Okay, yeah, so that's the problem. Okay, sensor response depends on oxygen concentration in enzyme layer. mm, If oxygen concentration is low, then uh, it 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 causes some errors. Okay, low oxygen concentration makes sensor response as if glucose in blood were low. Okay, yeah. So that problem must be overcome. Okay, the one good way to reduce oxygen dependence is to incorporate into enzyme layer a species substituting for oxygen is so-called mediator. Okay, let's temporarily stop here.